Hi there, and welcome to today's AWS webinar, Journey Through the Cloud. This is the third webinar in our series, and today we're going to touch on the use cases around storage and archive within AWS. My name's Ryan, and I'm a technical evangelist at AWS, and it's my job to speak to developers and business managers and to convey the benefits of cloud computing in a way that you can understand. So hopefully today you're going to learn something around these use cases and why storage and archive makes a great first step into the cloud. So the Journey Through the Cloud series that we've been running is based around the idea that we can articulate common stepping stones into AWS, stepping stones that our customers have taken to get started with cloud computing in a way that suits them and at a pace that suits them. So the idea being you can learn from the custom journeys that others have taken and pick up some best practices that may enable you to bootstrap your own projects and your own exploration of cloud computing. And today's topic is around storage and archiving. And today we're going to try and address and educate you upon the benefits and of the economics around cloud storage and cloud archive for what is a relatively simple to implement use case, because you can take advantage of storage and archiving in AWS without having to worry about compute resources, for example. You can simply use it as a storage platform. And by leveraging cloud computing, you can simplify the management of the life cycle around data assets. So what I mean by that, I mean that you can look at eliminating technologies and processes from your environment. You might be able to remove capacity planning for certain types of storage by moving that storage to the cloud. You might be able to remove particular types of technologies. You might be able to get rid of tape archive, for example. And generally you can improve the overall performance of your storage and archiving, and certainly reliability, by taking advantage of the cloud platform. So with that in mind, today's agenda is going to start at looking at why AWS for storage and archive, a high-level view around the reasons why it makes sense. We'll address some of the fundamental services, the building blocks that make up our storage and archive story. And then we'll take a bit of a journey through the use cases, examples and patterns that we have seen commonly within the customer base. And then we'll give you some ideas on where to go next to get some more information. So why AWS for storage and archive? Well, if you look at some of the customers that are using it, the use cases are quite varied. So ranging from storage of large volumes of data, such as NASDAQ with their EMEA service, where they have vast arrays of historical market and price information for the financial markets, and they build applications on top that allow people to go back in time and to do modeling upon historical data. So very large archive, if you like, for live applications, through to Spotify, which you may use and know, where they're storing their repository of music files and they're servicing that to over 15 million active users. SmugMug is a photo sharing application, online application, and they talk about saving $500,000 in storage expenditure and cutting its disk storage array costs in half by moving to cloud storage platforms. And then there's News International, so these are the guys that publish the Times, the Sunday Times and the Sun, and their digital assets driving their web applications and their mobile apps sit in cloud storage. And they're also collecting vast arrays of usage data around how people use their applications and websites that drives intelligence around what they do next in their development cycles. And you may be able to achieve some of these business and technical benefits from using cloud storage. So the first that customers will talk about a lot is reducing costs. So being able to slash storage and archive budgets in general is a benefit of moving to AWS Cloud. So you can reduce CapEx in terms of the money you have to spend on provisioning physical equipment, whilst dramatically increasing the scalability, because you can remove the cap on the scale that you can implement storage at within AWS. And you can eliminate the need for secondary sites by using cloud storage as a place to put archive as opposed to maybe a second on-premise infrastructure. You can eliminate the cost of running that secondary site. And overall you can reduce on-premise equipment, so the need to manage that and all the soft skills and all the costs that go with managing those on-premise archives. Our customers talk about eliminating 30% plus of the storage footprint that they're operating within their facilities. Another thing that you can achieve there, because storage and archiving tend to be tiered, there's different requirements around the speed of access. The amount that it will be opened, for example, in an archive will vary depending upon the type of data that's stored in there. So you can start thinking about different tiers of an architecture, consolidating. So you might better consolidate certain systems on premise to be, very high performance locally accessed data, and then push certain other types of classes of data into the cloud and reduce the overall on-premise footprint. Changing processes. So capacity planning is obviously a big one that comes with storage. So how much will you keep? How much is coming your way? How will that grow? How will that not? So changing the processes with cloud computing means that you don't really have to think about capacity planning. Because you can draw upon unlimited amounts of storage, you can eliminate the need to do that forward thinking, and you can also eliminate the need for provisioning for peak demand. Maybe you're a very seasonal business that has particular spikes in data collection or storage requirements, and you can eliminate the processes of planning for that and implementing services and systems around that. And you can remove aging technologies, so not only are there things like tape and backups for archive, but you can cycle out old disk arrays and slowly move storage capacity into the cloud and cycle out the maintenance around those older technologies. So driving those benefits are some fundamental services, and I'm going to talk about 3 services today that are basic building blocks for an awful lot that goes on inside the storage and archiving use cases, but also some of the technologies that are built on top of these that support storing data within AWS. The first of those is Elastic Block Store. And Elastic Block Store is really about very fast instance type disks, if you like, that drive the booting of OSs and drive the compute behind a particular instance. Now moving through to the right, we have Simple Storage Service, which is very fast object storage, and then Glacier on the far right, which is very slow but rare access, but high durability, low cost archiving. So there's like a spectrum of storage devices or services within AWS that meet differing needs in terms of performance and supporting the use cases behind them. So Elastic Block Store, a high performance block storage device, Simple Storage Service, which is S3, which is our object-based storage platform, and Glacier, our long-term archive. So looking at these in detail in turn, Elastic Block Store. Elastic Block Store is a persistent storage device, so it's a volume that's general purpose. You can format it to suit a particular file system and attach it to boot an instance. Its life cycle is independent of an EC2 instance, so it's persistent storage. And it's high performance, so the idea is that this is equal or better than a local EC2 drive, and you can also provision IOPS onto it. So if you have particularly intensive workloads, you can provision the level of I/O capacity that will be available for that particular drive. And EBSs come with a number of reliability features, so built-in redundancy within an availability zone. So any EBS volume you create and that backs an EC2 instance will be redundant within an availability zone. So you don't need to do RAID redundancy across the top of EBS, it won't give you any advantage. And the AFR, the annual failure rate, is better than a traditional disk drive of between 0.1 and 1%. EBS volumes scale to about 1 terabyte in size max, and you can have many of those volumes attached to an instance. And they come with features that allow you to create, attach, create backups of them, restore from backups, and obviously delete volumes. So they're a manageable virtual disk. And EBS is a fundamental back-end platform that drives EC2 compute instances, but then also enables you to move data around on drives and bootstrap different types of processes and different types of use cases, which we'll come to later. So the paradigm is a file system. Performance is very, very fast, average about 100 IOPS per volume or more, depending if you use provisioned IOPS. You can have up to 1,000 IOPS per volume with provisioned IOPS. It's redundant within a data center. It's only visible to your EC2 instances, so this isn't a publicly facing service. And it's priced upon the amount of data that you have allocated or the volume you have allocated. So if you choose to have a 1 terabyte drive and have no data on it, you will be charged for 1 terabyte of allocated storage. And a typical use case is a disk drive, and it drives a number of use cases. such as disaster recovery, such as archive and restoration processes within AWS. The next fundamental building block is S3, so our simple storage service, and this is a highly scalable object storage platform where you can store objects up to 5 terabytes in size and leverage 11 nines of durability. So it's highly scalable, it scales at a regional level, so when you choose to use S3, you're storing your objects in a region such as EU West, and it will scale in that region to meet your requirements. It's not a disk drive or a file system, it's a web store, so it's optimized for write once, read many, and it has an eventually consistent model behind the scenes because data is written multiple times across multiple physical facilities to ensure that we can achieve 11 nines of durability around your objects. And it's fast, it's very fast in terms of performance of a web service, it's highly durable, it's very economical. So it's an object store, not a file store. It's redundant across data centers. We have some public key, private key security as we do with all of our web service access. And you're charged for the amount of storage used as opposed to EBS, which is allocated. So typical use cases we'll come to later, but they generally drive the distribution of assets, digital media assets, to third parties or to applications within your environment. And we'll come on to some of those in detail. The last fundamental storage option in AWS is Glacier. So Glacier is our latest addition to the family, and it's about a long-term object archive. The idea being that we can store objects for a very long time that are infrequently accessed at a very low price point, but at the same durability as S3, so 11 nines of durability. And a comparison between Amazon S3 and Glacier is shown in this table. So the top two rows are Amazon S3 and also Amazon S3 Reduced Redundancy Storage, RRS. So you can actually choose to pay less for S3 and accept a lower number of nines durability. And the two comparisons here around Amazon S3 RRS across archive, backup and DR scenarios. So Amazon Glacier at the bottom is about long-term archiving, where you have infrequent data access. And think about if you were accessing less than 10% of data in your archives a month, that's what we really mean by infrequent data access. You can use policies to take archives or backup data and to move them that are maybe in S3 that aren't being touched very often, and move those cold data backups, for example, into long-term retention into Glacier. And the idea that in disaster recovery, you're going to retain a copy of data or system images that you're never going to touch unless it's the worst case scenario. So it becomes very cost effective to store these assets because you know you're not going to access them unless you really need to, and therefore you're not going to clear the cost of access. Because Glacier is really engineered to be very cheap for long-term storage, but you start to pay a price as you start to access that data. Okay, so there are three fundamental building blocks. So how do we put all this together into a series of use cases that we see in our customer base around storage and archive? So it's useful to think of a series of tiers in storage and to take us through a bit of a journey through the use case. And we're generally starting on the far left there with on-premise and moving through cloud on instance, object level and long-term storage on the right in orange. So on-premise you might have fast, locally accessible file systems driving workloads within the local data center or within your local offices and R&D labs and so on. And moving to the right into AWS, we start looking at EC2 based applications, so on instance storage of data on EBS volumes, looking at disaster recovery deployments where we have maybe pilot light systems running and synchronized in the cloud, ready to spin up in the case that you need them. Moving through object level distribution of data, distribution of maybe assets, static content for websites, sharing of media between supply chains, and creating a durable media store for archive of data or historical information. And then long-term storage such as system images, database backups, data archives that might be stored for many months, many years in a durable archive such as Glacier. All of these use cases have different performance characteristics, and these will drive how they are used in any of the scenarios that we might come across. So on-premise is very high I/O performance and a high network performance, locally attached disks maybe to workstations, storage area networks that are piped into your environments. Versus we go into cloud world where we've got things like provisioned IOPS on instance storage. We've got the services that surround them that are around backup and restore, which make them slightly different from using on-premise equipment. Through object level with good performance, high durability and scalability to long-term, very low price, highly durable archives. What I'm going to do is take a bit of a journey through these scenarios and how you get between them, or what you should do within them, and the services that apply. So the first thing, sort of bridging the gap between on-premise and on-instance, is getting data into the cloud. If you're going to store something in the cloud, or you have some on-premise storage and you want to move that to the cloud, how do you do it? It's your first building block, or your first hurdle you need to get across. So getting data into the cloud typically involves one of three services that we offer. So the first being Direct Connect, where you can create a dedicated bandwidth link between your site and the AWS region that you're interested in putting the data within. So this is, you're effectively renting a port on a private network by the hour, and you're going to get dedicated bandwidth and consistent latency for transfers of data to and from the cloud. Now that might be fine for certain volumes of data, but you might have many hundreds of terabytes of data that you wish to import or move into something like S3 for long-term storage, or move it into Glacier. So how do you do that? Now we have a service called AWS Import Export, where you can literally ship us your physical devices. So put them into a courier box and overnight deliver them, and they'll get plugged in our data centers, and that data will be uploaded into your account, and then we'll return the devices. And likewise, if you want data to come back, you can do it the other way around. So you should never underestimate the bandwidth of a speeding FedEx ban. So for very large data volumes, physical device transfer is the way to go. Then we also have a service called the AWS Storage Gateway. So this is a virtual device that you can grab from AWS and install locally on top of your disk arrays, and it will do a synchronization or snapshotting of those volumes that you have locally into AWS, and then allow you to restore from them if you need to, either locally back into disks that are running on your premise equipment, or into AWS, so you can start launching instances backed on the volumes that you created in your storage gateway snapshots. So this is a mechanism by which you can very easily start to leverage cloud storage for the backup archives that you might have on particular file systems you're operating internally. So Storage Gateway, shown here, essentially allows you to take snapshots of local volumes, stick them into S3 over a secure connection, and then restore from those snapshots as you need to. So a really great way of creating some redundancy in your local environment without having to maybe spend capex on creating redundant local storage, doubling up your SAN technologies with your file systems. You can create snapshots using the storage gateway and place them into S3. So Glimpse is a use case of using the storage gateway, and they were able to take a whole load of time out of managing their backups of their data in the cloud. So it's just hours to restore their systems. So they're particularly sensitive to their disaster recovery needs. The particular service they were offering meant that they needed to know and have the ability, a tested ability to restore data in their local offices as they needed it. And the storage gateway gave them the ability to create that cloud backup of their data systems that drove their internal applications, their processes, and restore them within just a few hours when they were needed, instead of days during their previous processes. Okay, so you've got some data in the cloud. Then what do you do with it, and how do you drive storage and archive use cases in the cloud? So the first thing that comes into play is disks and data on disks. So this drives most computing environments, whether it be an application, whether it be a file system, and EBS comes into play here. So EBS is an attached volume. So this diagram shows an Amazon EC2 instance being backed by an EBS volume or disk drive. and that will be a boot drive, for example, for a Windows or a Linux instance, and it will contain an operating system, maybe some application data, and some applications. Now, the EBS is a transportable volume, and this drives some of the use cases for or the changes in the architectural patterns that you can consider with cloud computing and storage platforms. So an EBS volume can be detached from an instance and reattached to a new instance. So shown here, I've thrown away my original instance that was booted from that volume, and I've created a new one from that drive. So if anything changes, or I need to move a data disk, for example, between instances, I can detach it from an instance and move it to a new one. So I create a transportable unit of either boot volume or data volume between applications. And of course you can have many volumes per instance. So I might have a primary boot EBS volume which contains my application stack and my operating system of choice for running an EC2, and then attach various data volumes that drive a particular application or a particular role of this EC2 instance. And then because I can create many volumes from a snapshot, I can create many instances that all have a particular image of data that might drive a particular requirement. So you can package data on EBS and then boot instances from EBS volumes. Now, a use case and a company that uses this is NASA and JPL, so they rely heavily upon EBS and bootstrapping, if you like, the EBS volumes with information. So they run a CMS called Raylo. It's running on Amazon EBS, and they're effectively creating a shared storage for Raylo using cluster file system across a pool of EBS volumes to create consistency on the performance they get, but also so that they can grow the number of instances running on top of their CMS layer across a shared file system, essentially across the EBS volumes. And this enables them to operate at significant scale behind their mars.jpl.nasa.gov website. So they operated something called NASA TV, and when Curiosity landed on Mars, or hovered above Mars and dropped Curiosity rover down, there was a broadcast of images and feeds from the JPL command centers and from satellites and so on that were tracking the spacecraft. And the demand upon their services was very high during that period, and they were able to scale up using a number of services, but fundamentally backed behind them was EBS using a cluster file system across the top. Okay, so that's disks and data. Then we move into things that are built upon those disks that we operate within AWS, and you can't really talk about storage without talking about databases. So database as a service is the next section. So we've got a few of these that you can use depending upon your needs. So the first and the most obvious is relational database service, which is a fully managed database. We take care of the management of that database, whether it be a MySQL, whether it be an Oracle or a Microsoft SQL Server database instance. We'll manage it for you and just provide you the functionality of the database. So you don't have to worry about the maintenance of that, the scaling of that, the security of that, the backup of that, and so on. Then we have SimpleDB, which is a schemaless database. For smaller data sets generally than something like Dynamo, which we'll come on to next, but a very flexible, great indexing and search technology across the top of a schemaless database where you can throw some data in, know it's going to be there, know it's going to be reliable, and know you're going to be able to query it back. So great for things like state, for sessions, and so on. Then we have DynamoDB, which is another NoSQL schemaless data store, but operates at a level of performance that was requested to certain customers, or so we saw within certain use cases and requirements that required very high throughput, consistent latency, regardless of the data volume stored within it. So it's a provisioned throughput database. So you decide how much I/O you require on a table, you dial it up essentially, and then we will shard and provision the hardware backed on SSDs behind the scenes to ensure that we can always offer average single-digit millisecond reads and writes, regardless of the volume and regardless of the rate that's coming in. So like EBS, DynamoDB is about provisioned throughput. EBS is provisioned storage, so you pay for that throughput that's provisioned whether you use it or not. Whereas RDS, you're paying on the instance hours that back a relational database, and SimpleDB, the amount of data and requests that go into it. So if you look at a traditional database with EBSs, you're going to create an application here. We've got an app server reading and writing data to a database server that we've hosted on EC2 and stored the software on EC2. And it's backed by EBS volumes. So we might have a boot volume, we might have a couple of data volumes that are attached to that instance. So with RDS, you essentially collapse that tier and you provide access from your app server to a database server, which is an Amazon RDS instance. And you simply create this using the command line tools or the console and choose your instance type and size and the database platform version, and off you go. You're given an endpoint which you can use. The RDS service comes with a whole bunch of stuff to make your life easier, and the first one of those, and I guess one of the most critical things around storage and archive, is the backup of your databases. So with RDS, what we do is we take backup snapshots and place them into S3. So S3 being the highly durable storage. And you end up with a series of point-in-time restorations that you can make from S3 to recover your database, and you can choose up to 35 days worth of backup history. You can also take entire instance snapshots yourself and do exactly the same process by storing those into S3. From those snapshots, all those point-in-time backups, you can then recreate a new database service. So here, this is a process that I've envisaged, a manual process of creating a larger database server. We can see the difference in height of those boxes. So maybe my database server is no longer sufficient in terms of size and compute resource to handle the load of my application server, and I wish to create a new one from the latest snapshot backup and double the size of the compute instance that's running that database. And I can simply do that through a resize exercise, restoring from a snapshot. And of course, switch over. So whether this be a manual resize process or indeed whether you're choosing to take advantage of the tick boxes which say make my RDS multi-AZ or multi-availability zone and therefore high availability configuration, if a failure is detected in that case, then it will switch over automatically and will reroute requests from your app server to the new instance. Just as if you take the old instance down and bring up a new instance, you're effectively initiating a manual failover as well. So we take care of all of that grunt work, so you don't have to do that by managing that storage platform or database platform yourself. The other sort of service that we touched on a minute ago was DynamoDB and NoSQL. So relational databases are fantastic, but they don't tend to track our requirement of predictable, consistent performance regardless of the scale that we're operating at. So shown here, performance of query, for example, we want a flat line regardless of the scale of our database. But in reality, relational databases, their performance of queries degrades as we get more data in them. So the scale of databases, the number of indexes that we have to create and manage, degrade the overall performance of a relational database platform. It's a fact of life. And to bridge that gap, you have to think about different provisioning new hardware, sharding your data, building clusters of relational databases, and then the associated problems of fault management across those clusters, and then start having to implement things like data caching layers. So traditionally, we might end up in an environment where we have here a model architecture. So we have a website fronted by a DNS, here Route 53 DNS, mywebsite.com, hitting a load balancer, in this case an elastic load balancer within the region, that distributes loads over some web servers that are sat in an auto-scaling group. So all good and fine in terms of model architectural best practice within AWS. You then have to think at scale around your data tier, and the back end here we've got database shards running on multiple database servers. And then we have in-memory caches. So we've got RDS masters, and we might have RDS slaves, for example, to manage those data shards. We've got Elasticache, for example, a memcached implementation, our caching layer Elasticache, doing an in-memory cache in front of those databases to offload some of the load. Now, if you find yourself in that situation and it's around maybe a couple of hotspots in your data model, What you can do is to shrink those and tables that are causing that performance bottleneck and place them into DynamoDB. So if you're able to handle a key value pair type schema within the data model and massage that around the rest of your relational data that you might remain in an RDS or relational data structure, then DynamoDB can greatly simplify that architecture. So you can simply have your web servers accessing DynamoDB, and then you provision the throughput you require on that particular data structure. So DynamoDB provisions throughput, so you dial it down or up depending on what you require. It's backed by SSDs, so the idea being to give you average single-digit millisecond latencies on reads and writes. It's strongly consistent, so you can be sure across that cluster that we're managing for you that your data will be the most up-to-date when you read it, and it's replicated across availability zones, so it's inherently fault tolerant. Like S3, it's operating at a regional level. Your table is stored at a regional level. We take care of the management of software instances running the Dynamo service behind the scenes in each AZ. And like most of our services, it's integrated into CloudWatch. It's secure and integrates with IAM, so you can lock down who can use it and who can't. And if you're interested in using Elastic MapReduce, it integrates with EMR for doing complex analytics on large data sets using the Hadoop framework. Shazam, a popular tagging application that you may have on your phones, use DynamoDB, and they achieve over 500,000 writes per second from their DynamoDB, and integrating with Amazon EMR, they're kicking out about 1 million writes per second out of EMR. So they were able to take away the problems of managing their own NoSQL data store across a complex cluster in AWS and shrink that estate into a NoSQL data store as a service, DynamoDB, take away all that pain and give them back their time and energies to focus on their applications, not on the operational management of clusters. Okay, so database as a service. Next point on our journey is we move away from instances and we get into object level serving and storage. So a slightly different concept from data on disks. At a really simple level, S3 is about storing stuff, and it stores stuff in buckets, shown here in blue, and makes those buckets available as a web service or a web call. So here I'm actually showing serving a HTML page from a bucket to an end user's browser. So this S3 is an interesting storage because simple's in its name, but it's not so simple when you get under the covers. Because to achieve this and the use cases around it, we do some special stuff. So you put data in it and we store it with 11 lines of durability. So we make multiple redundant copies in a region to achieve that durability, and we're automatically checksumming those objects, and when we detect issues across the number of copies we hold for you, we will automatically repair those issues. So you can be sure that your data is stored with integrity across multiple copies within a region, and your data won't leave the region. So if you choose to store in EU West or within an Asian PAC data region or AWS region, it won't move out of that region unless you say so. Now once you've stored your data in S3, we provide highly scalable web access to those objects for whatever purpose, whether that be that you're running a service like Dropbox, which Dropbox is backed on S3, or whether you're providing static images and Java and CSS files for your web applications, or whether you're simply storing backups of Oracle databases in S3, you know you can be able to get to those as you require them as the demand dictates. But it's not so simple, as I said. So it supplies a range of features beyond simple putting and getting of objects. So it integrates with something called CloudFront, our content distribution network. So with a single click in CloudFront, you can point a global distribution for streaming or for download at an S3 bucket, and that will be pushed out to our 35 plus edge locations around the globe so that if you have users accessing your data that's maybe held in an EU bucket in Sydney, they will access it from a local copy as dictates the demand upon that copy. You can secure it with access control lists, and that access control list also works across the CDN. We can do server-side encryption for you for free, so we'll do complex key management around each object having an individual key, and that key being encrypted with a master key that we cycle, and that comes for free, so you can encrypt your data with an S3 for no extra charge. You can use object expiries, so your retention on objects might vary. You might want to get rid of things that are older than 6 months. So you can set an object expiry and we will automatically remove objects. And shown in that previous image, we actually had a website being served from S3. So you can choose to serve a website, a static site from S3 without having to install web servers. It is a web service and it supports that, and you can do things like page redirection and so on, and you can support all the metadata that are required to drive a simple static website. And there's a whole bunch of other things that comes with it as well. So we support tools that allow you to browser upload into S3. We've got multi-part uploads. You've got signed URLs, so you can generate a URL token for access to an object. And this works again from edge locations as well as the core buckets. So you can generate access to an object maybe on a pay-as-you-go basis for your particular service, or because you need to have somebody authenticated in your environment, maybe by AD, to only have access to the object as opposed to somebody outside your environment. So it's not so simple. It's not simple get put. There's a whole bunch of stuff behind the scenes which make it a really attractive and flexible service for a whole bunch of use cases. And one of those use cases is Spotify. So if you use Spotify to stream music, you're streaming your content from S3. And Spotify needed a solution that could scale very quickly without incurring long lead times for upgrades. So they didn't want to have to do the capacity planning and the provisioning around storage for vast amounts of digital media. So they've used Amazon S3 to back that, and they'll talk about it being the most mature large-scale product on the market. So it gave them the confidence to expand the storage quickly with very high data durability without having to manage lots and lots of physical stuff, making that highly available and so on. Now, if you use Spotify as well, you'll understand that it's got various different tiers and models associated with it, and they've leveraged not only S3 features but other things within AWS and their application architectures to enable a pretty flexible business model around the technology and data they hold. So in essence, if you need to store something, S3 is a foundation building block. Okay, so that's object level serving and storage. And then the last point on this journey is cold storage and archiving. So this is where Glacier comes into play. So Glacier being very similar to S3 in some regards in terms of its concept that it has 11 lines of durability, all that same measurement of the state of different copies of your data, and the checksumming and repair of those all goes into Glacier just as it goes into S3. But it's designed fundamentally for reliable and cheap storage of data for a long time, so data with long retention periods, and data that's at very large scale that's infrequently accessed. And these are the things that drove us to develop Glacier in addition to the family of S3. The difference really is a lot around terminology as well and the method that you access your data. Some use cases, off-site archive. So the ability to take data off-site, archive it in a retained archive for as long as you need at a very cheap price point. So you might have enterprise data, periodic snapshots of very large data sets that you simply wish to store and that you don't have an expectation of accessing and only under an exceptional condition. You might have media assets that you wish to archive, and research and scientific data, maybe historical market data in financial services, medical data, seismic data in oil and gas and so on. Digital preservation is another major use cases where the fear of throwing something away because it might be valuable to future generations possibly drives the need to preserve those assets. So libraries, historical societies, charities, and also governments are increasing their efforts generally to preserve digital assets. Right the way back to your very first ZX81 video game through to user-generated content, websites that are out there. There are many different digital preservation archives being built, and Glacier is a perfect place to store those things because of its very low cost volume. And then tape replacement. So some of us might have tape archive machines and they're operating at scale, maybe even robots that are cycling those tapes in data centers. The Amazon Glacier is a cost-effective, competitive replacement, but it eliminates the pain of having to manage the tapes, manage the cycles, manage the capacity planning around those things by simply having an all-you-can-drink service. So how does it work? Glacier works in a similar way to S3 in that you put something into it and then you can request it back, and it has a similar concept to a bucket called a vault. So the first thing you do there, shown in grey, is you create a vault where you're going to store archives. And then you can configure on that vault things like an access policy, just as you might do on an S3 bucket. And then you can configure notification policies on that vault so you can be notified when things happen to that vault. That vault then becomes your place to upload archives, shown at item number 2. And you'd upload archives currently via SDKs. So we don't allow you to upload archives via the console. When you're ready to retrieve an archive, this is where the process really diverges from something like S3. So you request a retrieval of an archive in a vault, and they'll take about 3.5 to 4.5 hours after being requested to be available. And the process goes on behind the scenes that we initiate a job in order to retrieve the data in your archive from the vault. You can track that job, and then you'll be sent a notification of when that job is completed, where your archive is now available for download. And that's made available for 24 hours. Then you can pull that archive into your on-premise software or applications, or indeed push that into AWS to build an AWS environment off the back of that data. So a couple of quotes around what people are saying around Glacier. So Complete Genomics operate in a world where they have a legal requirement to archive patient data for many years, and that obviously comes with a big cost to them to operate in that business. So thanks to Glacier, they're able to provide cost-effective long-term storage that would be a barrier for entry for them to continue in that market and operate their service. And they're doing stuff around the sequencing of genomes, around cancer treatment, so an important aspect of research where the legal requirement was starting to hamper the ability for them to do their science. Another one around digital preservation is the New York Public Radio. So they think in terms of centuries when it comes to content retention, and the long-term preservation of their master archives is a pretty critical part of what they do at the New York Public Radio. So storing those assets in traditional media such as local discs or indeed tapes becomes expensive, and it also exposes them to corruption because tapes can get corrupted, and you have to manage those tapes in order to ensure that the integrity of the data on them is preserved. So moving the archives to Glacier is a better long-term solution for that particular use case. Okay, so we've taken a little bit of a journey through some of the storage and archive use cases, and hopefully you've seen how you can potentially use AWS services to maybe just store a bit of data, understand the cost and economics around the storage of that data, and see how that differs to maybe storing your data locally or archiving that data into things like tape in your local environment. But where would you go next if you want to find out more? Well, the first thing to say is there is a rich partner ecosystem. So there are many different software products, for example, technology products and hardware products that sit around the storage platforms within Amazon Web Services. So you might have Oracle, for example, as a database locally within your data center, and you can use Oracle's RMAN process to take backups of Oracle and store them into S3 as a back-end, highly durable storage platform, for example. There are also different types of gateway appliances. So like our storage gateway, there are different vendors out there that will use the S3 backbone, for example, to take or manage volume redundancy between different environments and massage them through S3 as a fundamental back-end store. So there are different types of software and products out there to help you get started. So do explore those, but also there are partners that can help you get going as well. So if you simply want some consulting advice, go to our website and have a look at the technology partners we have there. You can keep updated on what's going on within AWS by getting an RSS feed from aws.typepad.com. And there's also white papers at our /white papers that talk about storage and archive, that talk about backup, that talk about some of the database technologies that we have and the architectural patterns that are common around their implementation and use. So in summary, closing off today, there are a wide range of use cases for archive and storage within AWS, and it supports many different application types. So whether you're doing customer-facing online storage or maybe application storage, the top two at the top left there, where you might consider using S3 as a fundamental backbone, using things like our CDN to stream media out of it, or use the very low-cost storage of S3 to host arrays of application downloads to your customers around the world. Whether you're storing big data, so very large log files from application servers, customer data, usage data, placing those into cost-effective storage that are integrated with services that allow you to analyze that data, such as EMEA and instances and EBS volumes that are created under an Elastic MapReduce cluster to analyze them. Basic EC2 storage as well, so file storage, block storage, usage data around instances. So think of the NASA example where they're operating a shared file system across EBS volumes. And then backup and archive, data retention, how long you keep data, tape replacement with Glacier, offsite backup using storage gateway, and so on. And then the integration also of those things to on-premise storage. So through that partner community that I talked about, around NAS storage, SAN storage, offsite backups, there is a wide community of services available that help you do those sort of things. So in summary, AWS is a cost-effective place to manage digital assets. So whatever they are, whether you're storing things in databases, whether you need things locally as files on disks for high-performance access to some sort of compute requirement, whether you've got very large data that you just want to store because you think you're going to use it in the future and you want to archive that off, it's a cost-effective place to manage those assets. And the choice around the services that you would use are varied. And you're going to choose where to put something based upon the requirements for performance and the requirements for volume and the requirements for frequency of access. They're the main drivers around what sort of service you'd use to store a particular class of data. But it's not about a all or nothing cloud approach, because data assets can be mixed with stuff that's on premise, so you can integrate the cloud with on-premise services, whether it be simply taking backups of local volumes into AWS, or whether it be stringing together a model where you've used something like Direct Connect to connect on-premise applications and data to AWS applications and data. The options are varied. And at a number of levels, AWS storage and archive revolutionizes the technology behind long-term data retention. So S3, for example, with its multiply redundant 11 nines, at the price point that it's offered at, is something that's very, very difficult to achieve within your own facilities. Likewise, Glacier's cost-effective long-term storage at the same level of durability is something which revolutionizes the space of long-term archive and makes a real alternative to managing tapes and aging technologies such as that. So that brings me to the close of today's webinar. So as always, you can find out more at aws.amazon.com.